Okay, so here's a yo-yo problem. We have mass M and radius R. You hold the end of the string stationary while you release the cylinder with no initial motion. Here where it says use the energy considerations to find the speed of the center of mass of the solid cylinder after it has dropped a distance h. So we're going from here to here, and that is the distance of h. So what do you think we do here?
Basically, that equation that combines rotational and translational energy.
Okay, but we will get to, before we get to that part, which is the kinetic energy once it starts moving, let's look at the overall big concept. Anytime you hear the words conservation of energy,
kinetic energy and potential energy initially.
So kinetic plus potential should equal kinetic plus potential if it's conserved.
Mm-hmm.
So now that we know that, let's look at what's going on. Initially, what's happening?
Initially, you have no movement whatsoever.
So what is, if there's no movement, what do we know?
We know that potential energy is at its greatest.
And what else do we know? What is the velocity if there's no movement?
Oh, zero. Velocity is zero.
So that means that this whole thing goes to zero, and the potential energy at that point, so potential energy is equal to mass times gravity times the height.
Hmm?
So we would have the left side equal to mgh. And then on the right side, because
potential energy is zero.
Good. Because h is equal to zero, then u also becomes zero. Now the kinetic energy is going to be the big long equation that has, this is the motion up and down called translational motion.
Mm-hmm.
And then we have the rotational motion, which is what is?
Which is one half inertia center of mass angular velocity squared.
Good. All right. So if we're looking at that in this problem, we said these two equal to each other.
Mm-hmm.
This is what we're looking for. Oops, what is the inertia for a cylinder?
1/2 mass times radius squared.
And then omega. Any questions so far?
None whatsoever.
Okay. We can then cancel the masses. I'm going to multiply both sides by 2 to get rid of the fractions. Oh, actually by 4. Now, what do you see here?
I see velocity relative to the center of mass, which is also equal to r times omega, because of that equation we did a few problems back.
Okay, so if velocity center mass is equal to r times omega, how does that help me in this problem?
Velocity squared must equal r times omega squared, and you get everything condensed into.
Careful. You are in the process of eliminating the thing we're trying to solve for, because you told me to plug in r omega right here. And that would get rid of the VCM, which is what I'm trying to solve for. You have the right idea. We need to eliminate this and put it in terms of the term we're looking for, VCM. So use that relationship you told me and solve for omega, and you get VCM over R. And then plug it in for there. Okay?
Mm-hmm.
So what are we solving for?
We're solving for VCM.
Okay. So what do we need to do?
Well, what we need to do is we need to divide 3 by both sides.
Okay. And then?
Take square root of both sides.
Okay. Do you understand how that works?
I understand how that works.
Okay. So this is a good problem for a test because it combines Chapter 7 with the new material we're learning.